Okay, let's go fairly quickly through the theory of determinants. We're given an n by n matrix A, and the determinant of it, of course, is a scalar. And the function which takes a matrix to its determinant is a very important function. It has a number of important and useful properties. I'm going to mention a few of them here and then go through the fundamentals. So one of the most important properties of determinant is that it tells you when a matrix is invertible. The determinant is not equal to 0 if and only if it's invertible. That's an extremely useful fact, so it gives you an easy way to tell whether a matrix is invertible. And of course we've used it for that purpose quite a bit already. Another important property of the determinant is if you take a bunch of vectors and put them a basis and you put them into a matrix, then the determinant of that matrix, or its absolute value, is the volume of the box spanned by those vectors. And I'll draw a picture to indicate that. If you have three vectors like this, they span a box, or more precisely a parallelepiped. And the way you get that is by filling out the extra vectors as indicated in this diagram. And if you want to know the volume of this box, it's the determinant of those three vectors. And this is especially important in calculus, where it comes in the change of variables formula in the guise of the Jacobian. One more very important property is the determinant is multiplicative. If you have two matrices A and B, the determinant of A times B is the determinant of A times the determinant of B. And this is one of the most important properties of determinant. We use it all the time. There are many more, which I'm going to come back to later, but I want to start over now and focus on the really crucial ones. And there are really three fundamental properties of the determinant, and every other property of the determinant follows from these. So the first one is that if you have a matrix A and you switch two adjacent rows to get a new matrix B, then the determinant changes sign. Switching adjacent rows changes the sign of the determinant. Okay? And another basic fact is that the determinant function is linear in the rows. And what that means is that if you have a matrix like this and you think of it in terms of its rows, and the first row is the sum of two vectors v1 and w1, and well, you make two new matrices, one of them with v1 in the first place and the other one with w1 in the first place, then the determinant of A is equal to the determinant of B plus the determinant of C. It's additive in rows. And there's also the accompanying property that if you multiply a vector by a scalar, then the determinant multiplies by that scalar. If you multiply a row by C, then the determinant gets multiplied by C. And finally, the determinant of the identity matrix is 1. And this is really just a normalization. You could take it to be 2 or 10 or whatever you want, but it's most natural to take it to be 1. Well, here's a very important and remarkable result. It says that there is a unique function or mapping which takes any matrix to a scalar which satisfies properties 1, 2, and 3. So the determinant is completely characterized by these properties. And these properties, I'll remind you, are what happens when you switch rows, and the bilinear in the rows, and the normalization that determinant is 1. There's only one function which satisfies these properties. And that's a very powerful tool, and you'll see in a minute how we can use that. So now I'm going to run through a bunch of basic properties of the determinant and show how they follow from just 1, 2, and 3. So for example, if two rows of a matrix are 0, then the determinant is 0. And so let's see why that is. Just the only thing we're allowed to assume is properties 1, 2, and 3. Well, if the two rows are adjacent, you can switch them. And if you switch them, you don't change the matrix. But when you switch them, you change the sign. So the determinant of A must be minus the determinant of A. And so the only way that can happen is if the determinant is 0. If the rows aren't adjacent, what do? Well, after you can swap adjacent rows 2 at a time, and each time you do that, you just change the sign, and eventually you get the rows to be adjacent. And then once they're adjacent, you can apply the previous argument. And the fact that the matrix that you have might have minus the determinant from the one you started with doesn't matter. It winds up being 0 anyway. Okay, another property is if you add a multiple of one row to another row, that doesn't change the determinant. So why is that? So suppose you had a matrix with a bunch of rows, v1 through vn, and then you replaced row v1 with v1 plus c times v2. Well, by the property, the linear property, the determinant of the new matrix is the determinant of the original matrix plus the determinant of this matrix with cv2 in the first place. And now the first two rows are the same up to the c, but you can pull the c out by the linear property. So now you really get the first two rows are equal, and so the second determinant is 0. Alright, now we're going to show this important property that the determinant is multiplicative. And this is really nice because you don't have to do some crazy calculation. It actually follows from the properties. So first of all, if the determinant of b is 0, then everything here is 0. So it's true. So let's assume that the determinant of b is not 0. That's the interesting case. And let's define a new function, little d, where little d of a matrix A is the determinant of A times B over the determinant of B. Now, if the determinant really is multiplicative, the determinant of B's will cancel, and little d will just be equal to the determinant of A. So in order to show that's true, you just have to show that this function, little d, satisfies the three properties. And that's really easy. So, for example, if you change two rows, this little function, little d, is supposed to be 0. But that's clear because if you change two rows of A, you change two rows of AB. And so the numerator changes sign, but you haven't touched B, so the denominator doesn't. So that's easy. And similarly, if you want to check the linear property in the rows, that's very similar. And then finally, the determinant of the d of the identity is supposed to be 1. Well, d of I is the determinant of IB over determinant of B, and of course that's 1. Pretty neat, huh? That shows that the determinant is multiplicative without breaking a sweat. Okay, what's next? Suppose we have a permutation matrix. So remember, that's a matrix with a single 1 in each row and each column. Then the determinant is plus or minus 1. So for example, this permutation matrix, how do you figure out its determinant? Well, if you switch these two adjacent rows, you get to the identity. And since you did one swap of adjacent rows and the determinant of the identity is 1, the determinant of this thing must be minus 1. And similarly, this guy here, this 3 by 3 permutation matrix, you see how many adjacent swaps it takes you to get back to the identity. So here I do the swap of the second and third rows, followed by the swap of the first two rows, followed by the swap of the second two rows. And that gets me to the identity. And here I'm indicating which swaps I did along the way. And since it took me 3 swaps, the sign changed 3 times, and so therefore the determinant of this matrix is -1. And in general, you see that the determinant of a permutation matrix is -1 or -1, depending whether the number of swaps is even or odd. I claim that the determinant of a projection matrix is 1. Well, that's because p squared is equal to p. So the determinant of p squared is equal to the determinant of p, and you can cancel one of those, and you conclude the determinant of a projection matrix is 1. Okay, next up. Suppose you have a diagonal matrix, a1 through an on the diagonal and zeros everywhere else. I claim the determinant is the product of the diagonal entries. And that's just, you apply the rule that you can pull the scalars out one at a time. You multiply the first row, pull out the a1 from the first row and then from the second, and each time you do that you pull an ai out front, and at the end of the day you've got a1 through an out front and the identity matrix. So by repeated application of that rule you conclude this property. Also, the determinant of an upper triangular and a lower triangular matrix are the product of the diagonal entries. And that's because if you have such a matrix, you can row reduce it to the diagonal matrix. You can kill all of the entries above the diagonal. Another important property is that the determinant of a matrix and determinant of its transpose are the same. This one's actually a little bit trickier than you might think. Of course, you could give some proof using a formula, but I'd rather just give a proof using the properties. So let's assume the determinant's not 0, and let's use the LDU decomposition with the permutation matrix involved, and let's put the permutation matrix on the right side. So we write A is PLDU, where P is a permutation matrix, L and U are triangular, and D is diagonal. And, well, from that we can compute the determinant of A. It's the determinant of P times the determinant of L times the determinant of D, and so on. And we already know that the determinant of L and U are 1, and the determinant of P is plus or minus 1, and the determinant of D is the product of the diagonal entries. And now you take the transpose, and you get this. And when you take the determinant, well, U transpose and L transpose are still triangular, so those are still 1, and you get the determinant of D transpose and the determinant of P transpose, and D transpose is equal to D, so we get the determinant of D times the determinant of P transpose. Okay, so where are we? We have two formulas. The determinant of A is the determinant of P times the determinant of D. And the determinant of A transpose is the determinant of P transpose times the determinant of D. So all you need to know is you need to know that the determinant of a permutation matrix is the same as its transpose. And I'll let you think about that. That is true, and it involves counting the number of swaps that are necessary to get back to the identity. All right, so finally let's talk about Gaussian elimination. It's an important property of determinants that Gaussian elimination doesn't change the determinant because you're doing row operations. So in particular, you know that the determinant of a matrix is the product of its pivots. And in fact, that's one way of calculating the determinant, by using Gaussian elimination. And that gives a proof that the determinant is non-zero if and only if it's invertible, because you use Gaussian elimination to reduce it to a triangular matrix without changing its determinant. And we know that this matrix is invertible if and only if all of the AIs are not equal to 0, and the determinant is the product of the AIs. So there you have it. Okay, that's all of the properties of the determinant we're going to do for now, and I will see you in class.